Let us estimate pi using this circle and some basic probability. Draw a square around the circle such that it touches the circle on each of its 4 edges. Let r be the radius of the circle. Hence the length of edge of square is 2r. We know that area of circle is pi r square, and area of square is 4r square. Taking the ratio of areas, we get area of circle divided by area of square is pi by 4. Hence we can express pi as area of circle times 4, divided by area of square. Now we can use probability to estimate the ratio of area of circle to square without actually calculating it. Let us sample a large number of points randomly inside the square. Some of the points will lie within the circle, and others will lie only inside square and not the circle. The idea is to cover the square with as many points as possible, which can then be used to calculate the ratio of areas. For very large number of points sampled, ratio of areas can be expressed as number of points inside the circle divided by number of points inside the square. Since we need to sample large number of points inside the square, let us use a computer code. Let us assume our square's bounding coordinate is -1 to +1 in both x and y direction, which makes our circle have a unit radius. The code randomly assigns x and y coordinate between -1 and +1 to sample a point inside the square. Consider a sample point with coordinates 0.5 and 0.5. The distance from origin to this point is less than 1. Hence it lies within the circle. Consider another sample point with coordinates 0.75 and 1.0. The distance from origin to this point is greater than 1. Hence it lies outside the circle but within the square. Based on the 2 sampled points, the ratio of number of points inside circle to square is 1 by 2. Using this as the ratio of areas, we get a value of 2 for pi. This is far from being a good approximate value of pi, but we have used only 2 points. As we use more points, we get closer to a good approximation to pi. Looking at the code we have, we can define the number of points to sample. We have a loop to add more points, a function to assign x and y coordinates randomly. Finally, we keep track if the point is inside the circle or not using the distance from origin. If we use 10 points, we get a value of 2.8, which is not a good approximation. As we increase it to 10,000 points, we get a match with the first decimal. Increasing it all the way to 100 million points, we get a match with 4 decimal points. This demonstrates the power of large samples.